talking about the very last column. I'm not showing the last column at the moment because I don't want to reveal what the answer is, but I want to talk about the polar and nonpolar component of this, and we'll kind of intermix the polar and nonpolar aspect. If you have your notes, go ahead and grab those real quick, and it's near the back. I can't remember what page that's on, but it has a funny picture that looks like this. And honestly, the way that I teach whether a molecule is polar or nonpolar is unique. And I have to say that that's probably the best way to describe it, because it uses an analogy that's kind of gross. I hate to say it, but it does leave an indelible picture in your mind. Not something that's like X-rayed or anything, but definitely something that people used to do to other people in a very cruel way. When we talk about molecular polarity, now you're interested. When we talk about molecular polarity, we're actually talking about if I take a substance and I place it in either the colored water down here, that's just water, a student made this a couple years ago, or oil, which one will it dissolve in? And this solution here actually is very antagonistic. It doesn't like each other, because down here we have polar compounds, up here we have nonpolar compounds. And as you can see, they don't want to be together, okay? Which is kind of interesting. So we want to know what type of compounds we have, because a lot of the things that we work with, that we eat, that we drink, are polar in nature. We want, if we're eating something, we want it to actually dissolve within our body so we can actually use it. And then there's other things that we don't want to dissolve in our body so that we can just move it on out. All right, so I tell my son, he loves to eat salads, and he's like, it's so healthy for you to eat salads. I'm like, no, there's no nutritional value in that. It's for those of you who have difficulty moving things through, so to speak. I don't have that problem, so I don't need to eat salads. But those of you who do, that's why you eat salads, because it's very non-polar. We don't break that down, so it just moves on through. Okay, that's not the analogy I'm getting at, so relax. But when we talk about polar and non-polar components, we want to know the compound that we're looking at, will it dissolve in water, because water is polar, or will it dissolve in oil, something that is non-polar. And if we mix these two together, it gets very angry. And it looks kind of like a little smoothie, not something you really want to be drinking. But over time, and probably by the end of the hour, you're going to start to see some separation, but the next time you come back, you're going to see the oil on top, the water on the bottom, and then the very angry layer in the middle, because they have to touch each other. So when we talk about whether something's polar or non-polar, it has nothing to do with the types of bonds that the atom has. And unfortunately, we talked about covalent type of bonds, where it's a polar covalent bond and a non-polar covalent bond. That has nothing to do with whether a compound's polar or non-polar. So the way that I like to talk about whether something's polar or non-polar is we can talk about the technical terminology here, where we're looking at a dipole moment. That doesn't really do any good, because what happens is the electrons that are being shared between the atoms, the partial negative really likes to have those electrons closer to it than the positive. That's great and everything. But I like using what's called a tug of war analogy, and I don't think I have it on here, but let's use, say, a tetrahedral shape. Okay, what the analogy that I'm going to use is like back in the day, I mean way back in the day, they used to quarter people. Okay, not put them up in a house. They used to tie one arm to one horse, another arm to another horse, one leg to another horse, another leg to another horse. Chia, quarter them. Okay, yeah, that'd be a crappy way to die. I'm going to admit that right up front. Okay, but I like that analogy for this. Okay, so if we have our four horses here, and they're all pulling with the same amount of force, okay, but it's not strong enough to rip the arms and legs off, so to speak. But I want to know, is that central atom going to move? If all the horses are pulling with the same amount of force, will that central atom move? Have any of you ever done vectors? In other words, like if I have a force that goes this way, and then another force that goes that way, and then another force that goes this way, and another force that goes that way, that add up all those forces, the thing doesn't move. You'll get there. Okay, you'll have fun with that. But in this analogy here, if I have 4 horses pulling in all 4 directions, no matter how I hold this shape, the central atom won't move. So this is not an English class, but it does fit well. No move, nonpolar. So if all the horses are pulling the same amount of force, the central atom won't move. So that's a nonpolar molecule. Take a horse away. So now where I have a lone pair, there's no pull. So I have 3 horses here, will the central atom move? Yep, it goes down. So if I add up all those forces, that movement is this way. So if the molecule moves, and again, this is an analogy, if the molecule moves, it's polar. Okay? And we'll do some more things like that here in a second. But that's the analogy I want you to use. I call it a tug-of-war analogy. You can call it the quartering analogy. You can call it all kinds of things where you have these forces pulling. So let's say that I'm looking at a bent shape. This might be a little easier. Getting back to, say, looking at this structure here, where we have 2 lone pairs of electrons on top and we have 2 atoms on the bottom. Might be a little easier to see it with this shape, but if I have 2 horses pulling, will the central atom move? Oh, absolutely. So that's a polar compound. Okay, so most of the time, when you have lone pairs, it's about 95% of the time, when you have lone pairs, you have a polar compound. There's a couple exceptions. One of them is when you have an octahedral shape and you have 2 lone pairs. Now, again, the lone pairs don't push or pull, but if I have all 4 of those that form a square and it lies on the same plane, if I pull with all the same force, will that central atom move? No. So this is one of the 2 exceptions to where you have lone pairs and it's a nonpolar compound. So a square planar shape within the octahedral. The other exception is with that other weird shape, the trigonal bipyramidal. Okay, so within the trigonal bipyramidal shape, if I have 3 lone pairs, where I have my linear shape, again, I have 1 above, 1 below at 180 degrees. The lone pairs don't push or pull. That would be also nonpolar. Any other time you see nonpolar, or I'm sorry, you see lone pairs, you're going to have a polar compound. Okay. So now you can answer the questions on the far right of the column.
Mr. Craig.
Yeah.
So they're always going to be pulling in like a straight direction?
Yeah, they'll pull, and again, this is an analogy. This is the way that I learned or actually teach it, is that we're going to pretend that there's something pulling in a straight direction. So
it's not going to pull like.
Correct. It's not going to take, if there's only these 2, then the addition of that vector will be this direction. But this one's pulling that way, this one's pulling that way. Flip it around, that one's pulling that way, that one's pulling that way. So in this case with the tetrahedral shape, or any shape, okay, as long as there's no lone pairs and they're all pulling with the same amount of force, and again this is an analogy, then that means that the central atom won't move. Okay. So let's look at now the homework. Okay. So in the first one where you have the SEH2, now I'm not showing whether it's polar or nonpolar. I'm going to let you tell me if it's polar or nonpolar. So I'll actually do this. Okay. So we have our Lewis structure. There's 2 bonded pairs and there's 2 lone pairs, and it forms a tetrahedral shape and a bent shape. So would this be polar or nonpolar? Polar. Very good. Okay. So in that last column, you put either P or you'd write out polar. Okay. Now, yesterday, when you were working on the second one, I wasn't telling you about how boron is the moron. I wanted you guys to work on the octet. Okay. And also, what a lot of you were doing while working on this, you were really focusing on these numbers to help you determine the potential for whether it's a trigonal planar or a tetrahedral. What I don't want you to do, I don't want you to look at these numbers. Sometimes it works, sometimes it doesn't. So remember, when you're looking at potential, it's how many external atoms plus lone pairs on the central atom. Well, there's no lone pairs on this one. And also, if you had a 4 there, I'm not going to count it wrong, okay? Because I was going around making sure everybody was getting the octet rule. And you weren't just doing it on boron, you were doing it on like the sulfur, I think it was the sulfur trioxide, where you're just giving everybody 8 and not going back and doubling up. But later on in the year, we'll talk a lot more about how boron is the moron, and that it really only wants 6 electrons. But for the test, get in octet mode. Make sure everybody has at least 8, unless it's hydrogen, okay? And if you can remember that boron only wants 6, we're cool, all right? So in this case, we have a trigonal planar structure, and since there's no lone pairs of electrons, the name's the same. So looking at this, we're looking at a trigonal planar shape. Is that polar or nonpolar? Nonpolar, very good. Because all the external atoms, and I didn't say this, if you have, okay, if all the external atoms are the same and there's no lone pairs, it's automatically nonpolar, okay? So all the external atoms are the same and there's no lone pairs on the structure, it's always nonpolar. However, if you have at least one different external atom, at least one, it's going to be polar, okay? Because these have different sort of quote-unquote forces dealing with it, so different polarities there. And think about it, it's probably easy to think about it. These are equal horses, that's a pony, so to speak. So these 2 horses are going to drag that pony. Probably the best way to think about that. So looking at this, this is a nonpolar compound. Alright, looking at the next 2, where we have the iodate, the IO3 with the -1 charge. There are 3 external atoms and 1 lone pair, so is this polar or nonpolar? Polar, very good. Okay, because again, it's forming our tetrahedral shape with 1 lone pair. Okay. And since it does have 1 lone pair, the trigonal pyramidal shape is being formed because again, all those atoms don't lie on the same plane, so to speak. So it forms a little short stubby pyramid. And is this polar or nonpolar? Polar, very good. I think I may have asked that already. Looking at the silicon tetrabromide, so all the external atoms have their 8, therefore the silicon has its 8. So 4 shared pairs or bonded pairs, no lone pairs, tetrahedral. Is that polar or nonpolar? Looks like this. All the external atoms are the same, no lone pairs. So nonpolar, very good. So if all the external atoms are the same and there's no lone pairs, it's nonpolar. So will this dissolve in water or dissolve in oil? Oil, good. Water is always polar. That's why it's so delicious. Okay. Here we have our ICl3, and we're never going to have a carbon followed by an iodine. Okay, so that would be a chlorine. If you saw a C what looks like an I, keep it as a chlorine. So we have our 3 elements that have their 8, iodine, whatever's left, dump on the central atom, just give it legs. So we have 3 as our bonded, 2 as our lone. We have a trigonal bipyramidal shape and a T-shaped planar. So is this polar or nonpolar? Polar, very good. Whoops, pulled the wrong one off. Okay. So it forms a T shape that lies on the plane. Good, and that is polar. Okay, you guys are on a roll here. All right, so looking at I3 with the -1 charge, and again, stay aware of the charge because that's going to tell you if you're going to add or remove any electrons. And so we do have more than 8 electrons on this iodine, so I went ahead and gave it antennas. You could have given it legs, that's fine. Trigonal bipyramidal shape. Good morning. Okay, so in this case, it actually forms a linear shape that looks like this. So is this polar or nonpolar? This is one of our 2 exceptions. So we have the 3 lone pairs on the central atom, and these guys are opposite each other. So that's a nonpolar compound. So think about it, if you had your horses pulling in opposite directions, the lone pairs don't push or pull, so they cancel out. Yeah, Marissa?
Should we have rockets on that?
Yeah, your eyes were playing tricks on you. that what you were going to ask, Luke? Okay. Looking at the backside, and don't freak out if there's more than 4 elements. And again, the 2-dimensional plane looks a lot different than the 3-dimensional plane. Okay, so this has no lone pairs. Everybody has 8, so we have an octahedral shape with the lone pairs, and then the second name is the same. So is this a polar or non-polar compound? Non-polar, very good. All the external atoms are the same, no lone pairs on the central atom, non-polar. Here's our first noble gas, the big one, radon. Okay, so we have 4 shared pairs, 2 lone pairs, an octahedral shape that forms a square planar. Is this polar or non-polar? Non-polar, this is our other exception. So this one is one of the exceptions, and the I3 -1. So if you want to make a note that those are our 2 goofballs when you have lone pairs. So this is non-polar. Looking at the arsenic trihydride, is that polar or non-polar? Polar, good. So we have 1 lone pair, so it looks like that. Okay, so a polar compound. Any questions on the names here? Anybody like that? SO3, is that polar or non-polar? Yeah, I'm sorry. Go ahead.
For number 2, on the back side, I don't know like how you got onto in square.
Okay. So with this one here. Okay. So we have our shape that looks like this. And so I have my 4 external atoms plus my 2 lone pairs. So in that case my potential is 6. So with the 4 external atoms and then my 2 lone pairs, I'm going to work out a column 6. So this would, if it had 2 more atoms on top, it would form an octahedral shape. And since it has 2 lone pairs, then it forms that square planar shape. Okay. And did you have all your electrons on there?
Yeah, I just drew it.
Okay. Alrighty. So did we say that that was polar or non-polar? Why? Why non-polar? No lone pairs, and all the external atoms are the same. Now, let's also talk about a double bond, okay? Because this does have a double bond on one of the oxygens. So if it has a double bond, does it pull harder? No. Think of it like this. It's the same horse, except this horse has 1 rope, this one has 2. Just because it has 2 ropes attached to it doesn't mean it's going to pull any harder. It just means the rope isn't going to break as easily. But that horse is still pulling with the same amount of force as that one. Still going to rip that arm off. Okay. Lovely analogy. I love it. All right, again, the boron, if you went ahead and double bonded that, that's fine. So we have the 1 hydrogen and the 2 fluorines. Now there are no lone pairs on this compound, but is that polar or non-polar? Polar. Why? Different external atoms. So anytime you have different external atoms, whether you've got lone pairs or no lone pairs, if you have different external atoms, automatically polar. That's what makes this so easy. Okay. Polar or non-polar for the CHCl3? Polar, different external atoms. So we have a hydrogen and 3 chlorines. Okay. And then looking at the last one, and I try to confuse you on this one. If we say that, okay, I have it drawn like this, and some of you may have it drawn like this as well. Let's say that that horse is pulling with that amount of force, and that horse is pulling with that amount of force. And then we say that that horse is pulling with that amount of force, and that one's pulling with that amount of force. Could I talk you into thinking that this is now a non-polar compound? So that the hydrogens are canceling each other, the chlorines are canceling each other. Would you buy into that? What's going on? Is that polar or non-polar? What's that? Polar, I'm hearing? With a little bit of doubt in the voice? Polar? Why? Different external atoms. And what you cannot do, and I did that on purpose to get you to kind of think about that, we're not working in the two-dimensional plane, we're working in the three-dimensional plane. So these aren't canceling each other because they're at angles. They're 109 degrees away from each other. So if these are these red ones that represent the chlorines are the stronger horses, these are going to definitely drag these two. Okay, they're not opposite each other. So don't think in the two-dimensional plane when talking about polar and non-polar. External atoms, automatically polar. Okay? Yeah. It is. Actually, the last three are polar because we have a different horse here, so to speak. So we have a hydrogen and 3 chlorines. So it'd be like, let's see here if I can put that one together. So we've got our, say we've got our 3 chlorines, which are the white and the hydrogen here. The hydrogen's not pushing as hard as these guys, so it's dragging that one. But even easier, different external atoms, it's polar. Okay. All right, so again, the test will be structured a lot like this, where you'll have to draw the Lewis structure, tell me how many bonded pairs, how many lone pairs, the first name, second name, and of course, whether it's polar or non-polar. Okay. Any questions about this? So primarily what I want you to do today is you can build some of these if you need to see them, and work on the lab. The lab will be due on Monday when you take the test, so you've got this weekend to work on it. So that's what we'll spend the rest of the time doing today.